Hey everyone, this is Dr. Walker. This is video 105C on gravitational potential energy. You may be thinking, we've already seen this before, but in this video we're looking at the more general form of gravitational potential energy. Let's first consider the change in gravitational potential energy for a system consisting of a particle and the Earth. So we're looking at a particle that is moving from point A to point B, and it's at some distance from the Earth. So the distance from the Earth, the r, changes from r initial to r final. As it goes from point A to point B, it is experiencing the gravitational force due to the Earth. If we want to find its change in gravitational potential energy, we know that's equal to the negative of the work done by the gravitational force. We know this because we know the gravitational force is a conservative force. So if we take the negative of the integral of this gravitational force, this is what it's going to look like. We're going to plug in the gravitational force between the Earth and a particle that has mass m. We're going to integrate, and we're going to end up with this expression here. Negative g, mass of the Earth, times mass of particle, times 1 over r final minus 1 over r initial. Whenever we're talking about gravitational potential energy, we care about the change in the energy. Now, this expression does simplify to the expression that we are used to. We are used to using mg delta y. Remember when we have a surface and we have an object near the surface, we said it has some initial y. Let's say it's falling down to here. It has some final y. There's that delta y between the two positions of this object, and that's how you calculate the change in potential energy. Now, we always said, well, let's pick a reference level, right, where y was equal to 0. So we said y final equals 0, for instance, if there's an object falling. And then we would just say, okay, the potential energy of this ball, of this object, relative to the surface was just equal to mgy initial. Now we can do a similar thing to look at the potential energy of your particle when it's near or around the Earth. So it's not near the surface of the Earth, but it's at some distance from the Earth. The difference here is that we don't set the surface of the Earth to be our y equals 0 level. We set our 0 level to be when the force experienced by the particle is equal to 0. When is the force equal to 0? When the radius, when the distance r is equal to infinity. So we're going to say when your particle of mass m is very far away from the Earth, that's when it has 0 potential energy. So when we plug in r is infinity into the previous expression, right here, then we can see that this term will cancel out, and then we're just going to be left with this term. So we're saying the change in potential energy when an object goes from infinity to that certain position, A, for instance. We are measuring the potential energy from a reference level when r is infinity. The thing about this gravitational potential energy is that it is negative. Before we get to that, though, we can generalize this equation to not just be for a particle relative to the Earth, it can be any two masses. So whenever you have any two masses interacting with each other, which just means that they're at some distance r from each other, then they have this gravitational potential energy. So what about the fact that it's negative? If we graph this equation, it looks like this. The reason that the potential energy is negative is because that force is attractive. If you imagine a mass being very far away at distance r is infinity, which is over here, we said the potential energy is 0. What happens as this mass falls towards the Earth due to that attractive gravitational force? we know that it speeds up, right? Its kinetic energy increases, which means that its potential energy is going to decrease. So that's why when the object is at infinity, the potential energy is 0, but then as it gets closer, right, to the left here, closer to the surface of the Earth, the potential energy becomes more and more negative because it decreases. So that's how we can explain the gravitational potential energy being a negative function, because the force is always attractive. Let's take a look at one question. Which system has more gravitational potential energy? But we're going to look at the absolute value of the energy. Is it system A, where you have objects that have a mass of 2m separated by a distance 2r? Or is it system B, where you have objects with a mass m separated by a distance r? All we have to do is plug and chug into the equation for gravitational potential energy. For system A over here, we're going to have negative g times 2m times 2m. We have to do the product of the masses divided by the distance, which is 2r. So we're going to get negative 2 gm squared over r. Now for system B, we do the same thing. We're going to have negative g times m over r. So we can see which one has the larger absolute value is going to be system A. So a way to understand this, if we look at the graph again, the graph looks like this. So yes, system A is more negative, right, than system B. So system A might be over here, system B might be over here. So the larger magnitude of this potential energy means that it's going to take more work to separate these masses, right? If you want the distance between these two masses to be infinity, if you want to separate these two masses so that they're not under the influence of each other anymore, so that they have 0 potential energy and so that they're at a distance of infinity, right? You have to give system A here more energy to break those two masses apart from each other, because the energy is more negative, and you have to give it enough energy to reduce its energy to 0, or to increase its energy to 0, in order to separate those two masses.